So today we are only going to spend time on one of these just because of time, and I want to make sure that we have enough time to do some kinematic stuff as well, or some kinematics equation stuff. So we're looking just at 1G today. We'll go through 1H, or not tomorrow, Monday. Right now we want to look at part A. So the situation was a car traveling in a straight line to the right, starts from rest at a time equals 0. Time 2, the car is traveling at 4 meters per second. And at 4 seconds, the car is traveling at 8 meters per second. My first question for you is, are we talking about the cars that I have in the back, the little buggies? Can I use one of those for this lab or no? No. Why not?
You can't control the speed on there.
I can't control the speed. They don't accelerate. They don't change speed. So no, it doesn't work, right? So it'd be a different kind of buggy. To be very clear, so that we're all on the same page and we're all defining the same thing. What does it mean to accelerate?
Change speed, change velocity.
Change velocity. Yes. That is not a trivial statement. Do you want to say that to everybody? Because that was, yes. Go ahead. Say it one more time.
If you're turning, but you're not changing speed, you're still accelerating.
Indeed. Remember that in January. Okay? We're going to talk about that. Right now, so Jacob said that if you're turning but you're not changing speed, you are accelerating. And I said, absolutely, yes, you are. We don't talk about that case for a little while, just because of the way things kind of shake out. But, so for now, generally when we talk about acceleration, we're talking about changing speed. But that's not the only way to accelerate. Yes, change in velocity over time. All right, so in part A, you graphed some stuff. What kind of a shape did you get? You got a line. Now, hold on, I have a question. Because when you were rolling your balls down the ramp, you did not get a line when you graphed stuff.
It could be a flat surface instead of a angled surface.
Say that again?
It could be a double surface instead of an angled surface.
It could be, but okay, hold on, let me back up for a second. You had the ball that was going down the ramp. The ball was accelerating. And you predicted, like you were awesome, and predicted beforehand that the graph was going to look something like this. And then we graphed it and we, fought with Google Sheets a little bit, but you got a graph like this. So then now we're graphing another thing that's accelerating, and you don't get a curve this time. Right. So I want you to remember that. That's not another not trivial thing, right? This was displacement versus time. And when you graph on this one, it's velocity versus time. That's the thing. So what are they doing? They're linearizing, right? It's getting into a line. So you got a line, something like that. I'm just making this up. I'm just drawing pictures now. But you get the idea, right? I just want to make sure you're aware of that this was velocity versus time. And holy cow, if we go down here, it's going to walk you right through it. You know that on an AP test, it's not going to walk you through it, but we're getting there. We're getting there slowly so that we understand things. You use the slope. And oh my gosh, did you use data points when you found your slope?
Absolutely not.
Absolutely not. Wow, that is like super strong language. And it is very true. Never, ever, ever. What did you get for your slope, friends?
2.
2? 2 what? Bam. Okay. And the slope always, in this case, has a unit. So if I ask what the value of the slope is, I suppose you could say 2. But if I ask you what the slope is, it is 2 meters per second squared. Yes. Use the evidence above to make this claim. It's kind of like we're doing Mad Libs. Do you ever feel like that a little bit? Right? It's like, put in a number. Give me a number, right? Like, give me some, like you'd make up some really silly story, but it wouldn't be right. So let's do the right one. The slope of the velocity versus time graph is equal to, what was the number?
2.
Oh, and what units was it? Oh, and you can say meters per second if that makes you happy. Like if that, like you like the sound of that, that's awesome too.
I can even say
Meters per second or meters per second squared. Do you guys understand where that meters per second is coming from? Awesome. Is also the unit for
Acceleration.
Okay, that was kind of unimpressive. We're gonna try it one more time.
I think we're the only two that's really contributing.
I know, so I'm gonna ask for more help.
Acceleration.
Acceleration.
Oh wait, sorry, wait. Shh.
Let's try again. Meters per second is also the unit for.
Acceleration.
My grade table over here did not participate in that. We're gonna try it one more time.
That's why they're gray.
No, they're just wearing gray shirts. I'm not like ascribing a
color to a
feeling to
personality.
them, just that they're all wearing gray shirts today. We're doing one more time. I'm watching your mouths this time. Meters per second is also the unit for.
Acceleration.
Ah, it makes my heart so happy when you all think. Wow, that's nice. All right. Now, you have a little bit of space next to that. We're going to write something down that's really important. Let's write it down. Because when we write things down, we remember them better, right?
Yep.
The slope of a velocity versus time graph is what? The acceleration of the object. That statement right there is so important. I'm going to put it in a little something. Yeah. Some sort of something. You may want to get out your glitter pens or your highlighters or whatever it is right now. That is important. Don't forget it. All right. We're going to keep cruising. Part C, quantitative analysis. Hey, we're doing a little geometry today. So part B was first semester calculus. Part C is second semester calculus. This is really what you need to know, friends. Area is 1/2 base times height. You know that. You proved that in geometry probably a few times. It says rewrite the equation for the area of a triangle using symbols, numbers with units, and numbers with units, from the graph in part A between t equals 0 and t equals 4 seconds. So, what? We're looking at the triangle that exists right here, friends. This is the triangle I'm looking at. It is a right triangle. Hot diggity, that's cool, right? So the base is time, yeah? And the height is velocity? Is that okay? We want to know some numbers, though. You looking at numbers, I didn't have the numbers written down, so I need your help. So what's the base? 4, and not just 4, because it does say number with units. So what's the unit? What are the units that go with that 4? Indeed. So that's the base part. And the height, what's the value there? 8. 8 what?
Meters per second.
Awesome. Okay. And now we have to use our cleverness, because this right here is just doing geometry. But this is where the physics comes in, friends. So you've got 4 seconds times 8 meters per second. Look at those units. Seconds, meters per second. What happens to those units? What? They all cancel? There are no units? Just the seconds. The seconds say, see you later. So now we've got something that's just in what? Just in meters. And what kind of a thing do we measure in just meters?
Displacement.
Holy cow! That's an amazing thing. Now, this is a big deal, my friends. Because what we're doing right here is deriving another kinematics equation. So you watched me do 3 of them yesterday, right? You watched the video?
Yeah.
It was super exciting. You took some notes. It was great. Yeah. So here's the 4th one. It's coming right now. Here it is. Delta X. I use that for displacement. Here they're using X, but I like delta X. Delta X means it's a change in position. Change in position is equal to, what does this represent?
Time.
Time. And what does the other one represent? Velocity. And I don't know why, but I've just been programmed to switch them around, other way around. So I'm going to do that. So I'm going to say 1/2 the velocity. That's the final velocity, or the change in velocity, really. What'd you say? Are you like,
Time isn't the last variable, makes it comfortable.
yeah. I don't know. It must be some sort of like with our zodiac or something. Who knows? I don't know. I don't know. Anyway.
She's a Libra.
I'm not a Libra.
All right.
Are you not?
Okay, I'm sorry. I did not mean to digress there. The area. The area under a velocity versus time graph represents the what? It even gives you a hint here. We already did it. What does the area under the velocity versus time graph represent?
Displacement.
Okay, we're going to write it down, and then I'm going to ask for everybody to say it. So we're going to write it down here, and then we're going to write it down all again. I'm going to write it down over here next to my other one. We're going to say that the area under a velocity versus time graph is the what, friends? It's the... I heard at least one friend over there. Was he speaking for all of you? Chris, I did not hear your voice. I was right that I didn't? Okay, well, I'm glad. I'm glad that I didn't, miss it. So I'm going to say it one more time for everybody. Ready? Here we go. The area under a velocity versus time graph is the...
Displacement.
Did you speak?
Oh my gosh, we love this now.
Did you? Okay. I wasn't watching super carefully because I had my eye on him.
Here, do you part FNL?
All right, friends. Did you put a big box around that yet? You should. If you didn't.
No, wait, no.
All right, how we doing?
I forgot what I was going to say that I was forgetting to say in French.
I have a question. So how does the area
Oh my
actually
God, that just
represent it?
happened.
Like, do you find the area of the triangle and say?
Yeah, for sure. For real. Second semester calculus. Yep.
No, I don't get
It's
that.
actually
I'm
12
an
meters, 12 meters. I mean 6 meters.
Oh, that's the area under a curve.
Same thing. We still call it the
Triangles.
It's an integral, yo.
It's like the same thing.
All right, my friends. Come on back here, please. I am going to come around and give you something. I told you that I have a gift for you. I'm going to do this real quick right now. While you get out those little kinematics problems, those little 4 problems that you got yesterday, right? Here are some answers to those problems. I will put this up on Canvas as well, but there they are right there. Take a look. You may grab the thing.
Oh, here's my. Here's the problem.
You know how guys at least half.
No.
Jack, you're such a.
Go quick, go quick.
Wait, still the whole bunch.
Is that gift?
What?
That is your gift.
Thank Jacob. Hey, please.
And I
Stop
Jacob,
it.
will you
All right.
You know, I think I should be a boy.
Here we go.
Yeah.
So, while you're punching things, I'm going to have everybody listen, okay? This yellow sheet right here is exactly the same as the equation sheet that you will receive on May 8th. Is that when it is? I can't remember now. On the AP exam. It might not be bright yellow, but it is exactly the same, okay? So the reason that I give this to you is so that you are used to it, you are comfortable with it, and you know where to look. The reason I didn't give it to you before is because if I handed this to you on the first day of school, you're probably like, oh my gosh, because it looks a little bit scary if you don't know what's going on. But I will tell you that by the end of this year, you will be familiar with everything on this sheet. Okay? So I'm giving this to you today because yesterday, the video you watched derived the first 3 equations on the top left-hand corner. Okay? They might not look exactly like the way that I wrote them, but they're essentially the same. Okay? We'll kind of walk through them as we go, but I want you to be familiar with them. You may also, just for your sake, want to write down this equation as well, just because it's also helpful sometimes. I'm going to write it one other way, actually, though. I'm going to say delta x is equal to 1/2 V final minus V initial. Oh, I'm sorry, it's V final plus V initial, sorry, times T. It's actually a plus, sorry, not a change in. Now, besides that equation that you're just happening to write there, I wrote it right here. It's VF plus VI divided by 2. This is an average. So really where this comes from, besides up there, is this is an average of the velocity, and that's the same as the change in position over time. Okay. Besides that equation that you just may have written up there, you will have access to this sheet, this yellow sheet, on every single test and quiz that you take in this class. Okay? So I want you to use it, and I want you to be familiar with it, so that when you take a test or a quiz, you know exactly where you're looking. Okay? So this is that thing that you want to hold on to all the time. If for some reason you lose it, / you want to have 30 of them to put all around your house, it is available on Canvas. You can print one out. You can print 12 out, whatever makes you happy. Okay? Rainbow of colors, like whatever makes your heart happy is good in that kind of case. All right. So I put the answers to those 4 kinematics problems up there. I am happy to go through as many as we can between now and the end of the period. And if we get done, then we'll go through more things. I've got lots of stuff to do. Would you like a moment to talk to your table mates about these problems first? Or are you ready to get started with me right now?
Ready.
Ready? Says Hannah. Okay. Which one or which ones would you like to look at? Okay, let's do it. I'm going to move it over so that we can do it together. So this is the second problem, the bus slowing down uniformly. Now, I didn't actually come around and walk around and look at your papers from your processing of these problems this period, but last period I did, and I noticed that some people were trying to squeeze them onto the little tiny piece of paper. Okay? I'm going to tell you right now, friends, that I want you to get in the habit of using this guess method, and you can't fit the guess method for all 4 of those questions on the little tiny piece of paper. I want you to get used to it because that is the easiest way to figure out which equation you're going to use. Okay? Here we go. We're going to start with the givens. So I'll read the problem. You're going to prepare to put your hand up in the air. Everybody should be able to help with the givens. If you're one of those people that's kind of nervous and doesn't like to answer questions in class, then this is the time for you to do it because the answers are right in front of us. Okay? It says a bus slows down uniformly from 75 kilometers per hour, also 21 meters per second, to 0 kilometers per hour, also 0 meters per second, in 21 seconds. How far does it travel before stopping? Raise your hand for me if you can tell me one of the givens. You all should be able to tell me a given. Go, Spencer, go.
Time. You have to count 21 seconds is the time.
Thank you.
Sorry.
Fantastic. That's awesome. 21 seconds is the time. That's one given. What else you got? More hands. Go.
Final velocity is 0.
Final velocity is 0. Awesome. And 0 meters per second. I guess you could put it in any units that you wanted, right? As long as they were units of velocity. Go.
Starting velocity 75 miles.
It is. Did you? Yes, you said starting. Initial. Yes. Now, I totally agree with that. I could write that down. I will write that down to validate your statement. But I always have these little alarm bells that go off in my head when my units don't match. You see what I'm saying? Like kilometers? What? And hours? What? Like I could write this in kilometers per hour too, but that would be 0. But this one's listed in seconds. Top tip from a physics person who writes tests. If you've got an equivalent in parentheses, probably because they intend for you to use it. My guess is that when they wrote this problem, they just wanted to give you a speed that made sense that you could like maybe conceptualize. Like 21 meters per second. What does that mean? It means 75 kilometers per hour. So I'm going to write this as equal to 21 meters per second. Do we have more givens? Or is that it? That's it. Do I have any, what's my unknown? Displacement. Delta X. Okay. Generally in kinematics problems, you've got 4 things. So you have to find the equation that you have written down that includes all four of those things. Which equation do we have that includes all four of those things? The one that we just wrote down, right? Absolutely. So that one was, I think it was delta x was the way it was written, right? Is equal to 1/2 VF plus VI times time. All right. Delta x is already solved for, so that makes it pretty easy. We're just going to do our substitution. 1/2. Hot diggity, the VF is gone. See ya. So we just got VI, which is 21 meters per second, times the time, which is 21 seconds. I don't know what's up with all the 21s in this question. I don't know, I didn't write it. But I guess it makes it, yeah, whatever. Answer?
220.
Units are meters. I would strongly encourage you to do all of these steps. GUESS. That should have been in purple, but whatever. Right? Okay? Every time. Every time. Others of these four problems that you would like to go over? The last one? For sure. All right. A car starts from rest and travels for 5 seconds with a uniform acceleration of 1.5 meters per second squared. The driver then applies the brakes, causing a uniform acceleration of -2 meters per second squared. If the brakes are applied for 3 seconds, how fast is the car going at the end of the braking period, and how far has it gone from its start? There is a lot going on in this question, yeah? So first of all, before we do anything, can you kind of imagine what is happening here? Can you kind of picture the situation? Okay. So you've got something that's speeding up, speeding up, speeding up. That's kind of this part here. I'm going to break it down into some pieces. So it starts from rest, travels for 5 seconds with a uniform acceleration of 1.5 meters per second squared. Then, new part of the story, driver applies the brakes, causing a uniform acceleration of -2 meters per second for 3 seconds. Okay. Generally, if I have two objects or two situations, I'm going to write those givens down in kind of two columns to keep myself from getting too confused. Otherwise, I will. So situation 1, the part that I've got in yellow there, what's one of my givens? So, okay, hold on. I have an acceleration. I've got a time. What's the acceleration?
1.5 meters per second squared.
Okay. And how long does that last for?
5 seconds.
Cool. And do I know anything else in that yellow part? It starts from rest. What does that mean? Yes. Fantastic. Okay. All right. Second part of the story. What do I know in the second part of the story? What else do I know? We got a time. Okay. And what are we looking for? What's the first question?
How fast is the car going at the end of the braking period?
Okay. I just said when we did the other problem that we generally need like 4 things, right? Now, I only have 3 in each of these columns. I need to figure out a plan of attack. I don't know what to do. How fast is the car going at the end of the braking period? I don't know. All I know is this stuff. What can I do? Yeah, but I need 4 things. If you look at all 4 of those kinematics equations, they have 4 things in them. I only have 3 things listed. I have 6 things listed.
Do you have to solve for the final velocity in the left column and then insert that as the initial velocity for the second column?
What do you guys think? Does that make sense?
Yeah.
I'm thinking so. I need to find a final velocity for this column, for the stuff that's highlighted in yellow first. We can do that. I'm going to highlight this in yellow. This is the yellow part. We'll do the yellow part over here. Do I have an equation that goes with acceleration time, initial and final velocity? Yeah, I do. It is, where do I need a green here? We'll do this one.
What are the subscripts X and XO?
Yeah, let's talk about that, shall we? For sure. So the equation that I'm seeing that has the things in it is the very top one that's printed on there. That it says Vx equals Vxo plus AT. So when College Board writes this, they're kind of making it in a very specific way. So the x's refer to a one-dimensional problem. So right now, that's all we're doing is one-dimensional problems. But soon, we're going to break into 2 dimensions. And the thing that this is telling us is that the velocity here and the velocity here, and is there an x on that one too? There is. Yep. These 2 velocities in this acceleration all have to be in the same direction. Okay? For our purposes right now, we do not need those x's. And I will be completely honest, when I write this equation out, I never write the x's. Okay? So that's the first thing. What does the little O mean? Initial. I write I and F. That's what I do. Here, they just do velocity and velocity naught. V naught is what they call that. So my version of this would be VF is equal to VI plus AT. Often I will actually write this as A is equal to VF minus VI over T. This is the way that I know it and love it and understand it because it's a change in velocity over time. Okay. This is just the VF is solved for. It's the single line version. And it's actually convenient in this case. Okay. So now I can use that. And I can do a little bit of algebra. Get rid of that VI. And now I've got VF is equal to AT. I can do a little substitution. So I've got 1.5 meters per second squared times the time of 5 seconds. And the velocity of the car, after it's had this positive acceleration, hey, is it going to be faster or slower than 0? Faster, right? Because a positive acceleration is going in the positive direction, speeding up, speeding up, speeding up. 1.5 times 5 gives you?
7.5.
Yeah. What are the units?
Meters per second.
Meters per second. Are you saying that because you know it's a velocity or because you can see it? It's there. Meters per second squared times seconds. One of those seconds cancels. Yep. So it's meters per second. So this is the final velocity for the yellow part, right? For the positive acceleration part. That is going to go in here as the initial velocity for this part. Okay. Then we can plug it in. It's going to be the same darn equation. Not very exciting, really, when it comes down to it. So the blue part I'm going to do down here. So I've got V final is equal to V initial plus AT. It's almost the same, except now that initial velocity doesn't go away. Are y'all okay with this? This is how I say when something goes away to make my life easier, but make sure that I know that it's going away. Just cross it out. Okay. In this case, it doesn't go away, though. I've got 7.5 meters per second plus an acceleration of, oops, I didn't write a plus there. Let me do that. Plus negative 2 meters per second times 3 seconds. How are we doing? We okay? So we do some math there. One little note here, don't forget that negative. Okay? Because the car was going 7.5 meters per second, and it's going to slow down, right? That's the whole game. Is it going to slow down? It's going to slow down by 6 meters per second, it looks like. So I've got 7.5 minus 6. I can do that without a calculator. What is it? So that's the answer to the question that was actually being asked. Oh, but then there's another question. Rats. Not quite done. What is it? What is the total displacement? They really snuck 4 questions into one in this one. Did you see this? Right? They have the yellow question that feeds into the blue. And then for this one, you got to find the displacement for both pieces. So it's the same problem, or not, it's a different problem, I suppose, in this case. So now I want to know the displacement. Strong recommendation coming from Ms. Carbeling. Doesn't happen, well, it does happen a lot, actually. Strong recommendation. Do not use what you calculated if you don't have to. So I would use A, T, VI, and delta X. Do you have an equation that has those 4 things in it? Yes, I do. You're like, I don't know if I do, because these equations look really weird and scary. Let me help you out. Look at that second one. The second one may be the scariest looking equation from kinematics, but it is, in fact, my very favorite. Okay, let me tell you why. Well, I just like it because it's useful and we use it a lot. The x minus x naught, what is x naught? It's not nothing. Initial position, right? I usually move that over and I just call this delta x. Change in position, displacement, is equal to, remember those little x's don't matter. So this is really v initial times time plus 1/2 a t squared. This is the one that you're going to write down all the time. And I'm going to ask you what equation you're going to use. You said the big one, scary one. I'm going to say, yep, you're right. Because we use it a lot. Okay? You get to know it and love it. It's a great one. Okay? You're going to plug stuff in. Oh, wait. That goes away for this one. Yay! See ya. Oops. VI goes 0. You can plug it in to figure out your displacement. So you've got 1/2. What was the acceleration? 1.5? And the time was 5 seconds.
8.
Oh, you're telling me the answer?
No. Wait.
What did I do?
Wouldn't it be the time the total time?
No, because I have to find the displacement. You have to do it in 2 pieces.
Oh, duh.
Right? Does that make sense?
Yeah.
Yeah. So I have to do this part first. Okay, and then I'm going to add that to the other piece. Yeah. Do we get a number here?
18.75.
Awesome, thank you. That's the first piece, and we'll have to add it to the second. Is that making sense? It's a little bit arduous. I'm going to let you know that I think this stuff is really important, but to be honest, kinematics problems, while fun and exciting, are not the most important thing that you're going to do, okay? So I want to make sure you know how to approach them, but really what we're going to focus on Monday is how to graph them, okay? Because that's what really matters. We're getting close, and I would love for you all to put your chairs and all the rest of the chairs up. Don't lose that yellow sheet. That equation sheet is your key to happiness in AP Physics now, sometimes.